Altitude 10,000 meters, and the tiny bent piece of metal outside your window is hiding a secret that once nearly tore planes apart in midair. Engineers spent decades fighting an invisible monster on that wingtip, a truck-sized tornado that literally grabs the plane and drags it backward. Their first fix was so dangerous it made wings fold like butterfly wings and shake violently until parts ripped off during flight. Airlines now pay millions, even performing open surgery on flying machines, all because of one forgotten patent and a terrifying secret stolen from birds. Stay until the end because what this bent metal really does will change how you see every flight forever. Altitude 10,000 meters. A passenger jet glides above the clouds at nearly 900 kilometers per hour, burning tons of fuel every hour. If you glance out your window right now, you'll notice something strange about the wings that most travelers completely overlook. The wingtips don't end in a clean, straight line. They curve sharply upward, as if someone deliberately bent them before takeoff. At first, it looks like a tiny decorative touch, a cosmetic detail that surely changes nothing about how the aircraft flies. But here's what stops you cold. Airlines pay millions of dollars to install these small pieces onto their planes. Some carriers even pull perfectly good aircraft out of service years later, sending them back just to add these curved tips. So the question practically screams at you. Why spend a fortune on a fragment of metal that also makes the plane heavier? To understand this obsession, you have to descend into the physics, into the exact spot where an invisible enemy quietly hides. Picture yourself in a moving car, sticking your hand out the window at high speed. The air slams against your palm. At those speeds, the once transparent air transforms into a solid, unforgiving wall. For a jet weighing many tons, that wall becomes a real barrier. The engines roar at maximum power to punch through it, quite literally burning buckets of expensive kerosene every single minute. Airlines lose millions to this resistance. But the most vicious culprit isn't hiding at the nose of the plane. It waits at the very tip of the wing, at the farthest edge where the metal finally ends. The entire theory of flight rests on one elegant trick. You have to create a difference in pressure across the wing. As the jet gains speed, the wing slices the air, forming a dense cushion underneath that pushes the machine upward. Above the wing, something else happens. A zone of near emptiness forms, acting like a giant vacuum cleaner sucking the plane into the sky. But right at the boundary of this process, engineers ran into a devastating flaw, a relentless leak of precious energy. Nature despises emptiness. It always fights to balance out pressure, no matter what stands in its way. Imagine suddenly opening a shaken bottle of soda. All the gas rushes from high pressure toward the opening with a violent hiss. Exactly the same thing happens at the wingtip, precisely where the metal stops and the air has nowhere left to cling. The dense air from below rushes fiercely upward into that zone of emptiness, twisting as it escapes around the edge. This escaping stream spins into an invisible vortex, a swirling tornado roughly the size of a truck. That stormy trail follows the aircraft for kilometers, an unseen wake of chaos ripping through the sky behind it. In aviation, this effect has a name: induced drag. But in reality, it works like a tightened brake cable. The tornado literally clings to the tail, dragging the airliner backward with a stubborn, invisible force it can't shake off. To overcome this hidden pull, the engines spin harder and higher, wasting tons of fuel on nothing but resistance. So the curved wingtip is not decoration at all. It became a purely economic decision to cut that brake cable. The designers of the past attacked this problem in the most obvious way imaginable, and their logic seemed flawless. If air spills off the edge of the wing, then just make the wing incredibly long, pushing the tip far away. The idea was beautiful. Move that spinning vortex so far from the fuselage that it weakens and simply fades to nothing. The mathematical calculations promised an enormous breakthrough. But the first attempt to build it in metal hit a brutal wall. To understand why the dream collapsed, imagine holding a long, thin wooden ruler right at the very edge. If you flick the opposite end, the ruler snaps easily between your fingers. That long wing became exactly that dangerous lever. In flight, the air pressed on those extended tips with such force that the joint where they met the body suffered terribly. Extreme fatigue built up in the metal. A frightening danger emerged with every passing flight. At the first serious burst of turbulence, the wings could fold upward like the wings of a butterfly. To save the structure, engineers would have to make the wing base impossibly thick and heavy. But then the plane would weigh as much as an iron bridge and never rise off the ground at all. And even if you ignore the strength problem, an even more down-to-earth obstacle shattered the whole idea completely. Picture an enormous off-road vehicle, so huge it can no longer crawl through narrow streets or fit any parking space. The same thing happened at the airports. The new giants with their wide wings no longer fit standard gates. They clipped the light poles along the taxiways. They couldn't pass their neighbors or squeeze into the maintenance hangars. Rebuilding thousands of airports across the entire world for one single aircraft model. That was pure economic madness. The industry stalled completely. A different path was needed. Calm the vortex while keeping the plane's dimensions unchanged. Then researchers made a paradoxical move. Instead of looking forward, they turned around and dug into old historical archives. To their surprise, they found something forgotten there. A patent from British scientist Frederick Lanchester, filed astonishingly early. This man described the concept before the Wright brothers ever made their first flight, 6 years ahead of aviation itself. Lanchester proposed mounting simple, flat, vertical plates on the wingtips, standing straight up like blank walls against the air. These barriers were meant to block the path of the dense air and stop it from spilling upward around the edge. Inspired, the engineers decided to try the idea in metal, bolting rigid vertical shields onto the ends of the wings. During the earliest tests, these plates genuinely did control the flow beneath the wing. But then, a nastier problem appeared. The straight plates worked like a powerful brake. Imagine opening an umbrella against a fierce gust of wind. It doesn't let the air swirl, but it yanks you backward with terrifying force. The shields fought the plane's motion. Worse, these heavy plates loaded extra weight onto the edges of the structure. At high speed, that triggered dangerous shaking. Pilots call it flutter. The wing trembled and twisted violently, dozens of beats per second, as if waving its hands. Such uncontrolled vibration creates critical loads, strong enough to tear structural elements apart right in the middle of a flight. Some aviation circles still whisper a theory that the flat plates were rejected only to avoid paying for an old patent. But that's just a myth. Real physical tests prove the simple flat sheets were both ineffective and genuinely dangerous. The vertical washer project was declared a failure and shut down completely. Dry formulas and crude barriers no longer worked. The solution came from a completely unexpected direction. Researchers turned away from their drawing boards and looked toward living nature. They studied the ones who spend their entire lives in the sky, masters of the air long before humans arrived. In the mid-1970s, inventor Richard Whitcomb at NASA decided to change the entire approach to the problem. He realized humanity was trying to reinvent something nature had already built and perfected across millions of years of evolution. Whitcomb set the blueprints aside and focused entirely on the anatomy of large birds of prey, the tireless soarers. These birds can circle the sky for hours without a single flap of their wings. He needed to know their secret. Studying the feathers of eagles and hawks, he discovered something remarkable. In long flight, they never hold their wings perfectly straight. The outermost feathers curl almost vertically upward, spreading apart to form a kind of elegant, feathered fan. To understand how this works, imagine trying to block a powerful jet of water with one wide, flat palm. The water bursts around the edges, exploding into bubbling, chaotic splashes that spray uselessly in every direction. But if you spread your fingers, that single stream splits into many small, weak, perfectly calm little flows. The birds do exactly this. Their spread feathers slice one dense vortex into small, harmless streams, and the energy loss nearly vanishes. Based on this discovery, Whitcomb proposed a brilliant engineering solution. Instead of a flat shield, he designed a tiny curved wing. It was a miniature, smoothly bent petal, carrying its very own aerodynamic profile, shaped like a falling drop of water. He gave the design a teardrop form, tapering toward the top with a barely noticeable slant to the side. The first mock-ups looked strange, almost awkward. But hidden inside that odd geometry sat the main physical secret of it all. When the invisible tornado starts twisting around the wingtip, that furious stream strikes the curved winglet head-on, but it doesn't hit straight. It strikes at a cunning angle, exactly like a slanting wind meeting a tight sail. Imagine a sailboat that can use a crosswind to move forward, sailing almost against the very current pushing it. Here, the same paradox unfolds. Instead of slowing the plane, the vortex's energy begins to shove it forward. The designers pulled off the impossible. They took their greatest enemy and transformed it into extra thrust, driving the airliner onward. In the first wind tunnel tests, the small models showed extraordinary results. Sensors recorded a massive drop in air resistance. But a plastic model in a quiet laboratory is one thing. Trusting this fragile part on a multi-ton machine is another entirely. In the real world, the tiniest error in the strength calculations stood one step away from turning into catastrophe. And the invisible vortex wasn't just draining money through wasted fuel. It was long considered a genuine hazard of the skies. This hidden trail is called the wake turbulence. It follows behind the aircraft, lurking in clear sky like a treacherous trap. To grasp the danger, picture yourself in a small inflatable boat as a giant ocean liner races past you. The furious wave left in its path could flip your little boat over in an instant. The same happens in the air. The most powerful vortices are born behind the huge double-decker jets. Their invisible wake can linger for minutes. If a small plane crosses that unseen trajectory, even 3 minutes after the giant passes, the consequences can be severe. The airflow there is so violent it can shatter the stability of any craft that wanders into it, throwing it off course. Because of this, controllers were forced to hold long pauses between takeoffs, keeping planes idle beside the runway. Aircraft stood waiting near the strip, creating enormous traffic jams on the ground, while precious minutes and money slipped away. Then came the moment of truth, when the curved tip technology faced its first real test on a heavy machine. Engineers had to find out if a fragile-looking bent wing could truly destroy that dangerous, twisting rope of air. To see it, testers flew aircraft through artificial curtains of smoke so the cameras could capture the shape of the swirl. When researchers first studied the footage, they were stunned with joy at what the images finally revealed to them. Where a destructive, twisted cable of air once raged, now only a faint, quickly fading trail remained behind. The winglet had done its job magnificently. The instant these results were published, airlines calculated their future profits and demanded wings now. But nobody wanted to wait 10 years for factories to build entirely new generations of aircraft. They wanted it immediately. Executives demanded the curved tips be installed on planes already flying. At first glance, that task seemed almost simple. In reality, engineers faced incredible difficulties right there in the repair docks, working on delicate, fully assembled machinery. Imagine needing to fasten a heavy iron nut onto the very edge of a thin plastic ruler. It bends instantly under the weight. A modern wing is a fantastically complex mechanism, hiding fuel tanks and control systems inside its slender frame. You couldn't simply drill a hole and screw the part onto the edge. The curved tip added hundreds of kilograms. That extra mass pushed the design to its limit, creating dangerous bending loads right where the wing meets the body. To eliminate the risk of failure, engineers performed real surgery on the open wing, peeling back the skin entirely. They reinforced the internal support beams and recalculated the whole balance. The slightest mistake could unleash violent shaking at high speed. Yet hundreds of these complex conversions in the hangars finished successfully, and the modernized airliners returned to regular flights. So, what did this global transformation actually achieve? Look no further than the cold, undeniable numbers. The standard winglet cuts average fuel consumption by roughly 5% on every single completed flight. It sounds small, but to picture it clearly, imagine thousands of giant sports pools filled to the brim with liquid kerosene. That is how much fuel the planet saves every year. In a world of ever-rising prices, that 5% becomes billions of dollars. Beyond the money, the project brought priceless benefits to the planet itself. Harmful emissions dropped by millions of tons annually. The air above our cities grew cleaner, and the flights themselves became far safer than they ever were before. The weakened wake let controllers shrink the gaps between takeoffs. No more endless waiting on the runway. Now planes can land and depart one after another, finally dissolving the massive traffic jams at the world's busiest airports. But human thought never stands still, and today you're watching another turning point in this technology unfold above you. Whitcomb's angular winglets are slowly becoming history, making way for even more advanced and graceful creations. On modern airliners, you can increasingly spot elegant tips shaped like the fin of a shark, slicing cleanly through the air. On the newest models, engineers install split tips that branch in two directions at once, curving both upward and downward. Each of these steps reclaims a few more hundredths of a percent of efficiency from the restless air. Every line and every hidden curve on a giant fuselage is dictated by the harsh laws of physics and years of relentless work. The designers unraveled the ancient secret of a bird's wing and tamed the invisible chaos of the airstreams. So the next time you rise above the clouds and look at those tips bending calmly toward the sky, remember what they hold. What do you think? Did aircraft lose part of their beauty when they abandoned perfectly straight wings for savings and ecology? Or is engineering perfection far more important than outward elegance? Tell us in the comments what you believe.